Physics Lab 4 dealt with oscillation. The goal of this lab was to observe the motion of a spring mass system and analyze the energy changes throughout the spring's oscillation. In this specific lab, we were tasked with analyzing this video of a mass as it swung at the end of a spring. We are using Newton's second law to predict the motion of the mass through the forces being applied to the mass at all times. Newton's second law states that the force is equal to the change in momentum over the change in time. So, the net force of the swing is equal to the mass times the change in velocity over the change in time. The other main fundamental principles include the energy principle, which states that the work done by all the forces acting on the mass equals the change in the energy of the system. Another important thing to note is as potential energy increases, the kinetic energy tends to decrease. Lastly, this lab deals a lot with oscillation, which is the periodic movement of mass back and forth either horizontally or vertically. Using the sample video provided, Tracker was calibrated to have the origin where the spring is attached, and a length of 0.7 meters was set to be the distance from the origin to the mass when released. The x-axis was set to measure the horizontal movement, and the y-axis was set to measure the vertical movement of the mass using the center of the mass as the point being tracked. The spring constant K had to be calculated based on the period determined from the video in Tracker using the formula 2 pi times the square root of m over k equals t. This gave us the K value of 6.734. The relaxed spring length was calculated using the found spring constant to be 0.11 meters. In the code, the mass had to be set to the given value of 0.402 kilograms, and the initial position was set to match the initial conditions on the Tracker video. The time between frames was also adjusted in Tracker. The spring constant and gravitational constant were set, and the calculated K value and relaxed length of the spring were added into the code as well. Next, the gravitational and spring potential energies were set with their corresponding formulas. The kinetic energy was also set to equal 1/2 mass times velocity squared. Their energies were summed to equal the total energy. Next, the velocity and the position of the mass had to be updated, and the change in each force was set to equal the final force minus the initial force. When I ran the code, I selected a CSV file containing my recorded X and Y positions of the spring taken from the Tracker data. As I ran the code, the predicted position of the mass was very similar to that taken from the experimental data pulled from Tracker, with both of them oscillating back and forth. The differences in the predicted and experimental data are likely due to human error. In the change in energy versus time graph, the kinetic energy is shown as the blue curve, the gravitational energy is shown as the red curve, the spring potential energy is shown as the green curve, and the total energy is the orange line. As supported by the energy principle and the relationship between potential and kinetic energy, the kinetic, spring, and gravitational energy, when summed, created a total energy close to zero for the entire oscillation, because as the kinetic energy increased, the potential energy decreased, and vice versa. This lab is relevant because the graphs and code show how the basic principles of physics show Newton's second law and the energy principle, and how both can be used to predict an object's location and break down the motion of a mass into specific components. The graphs appeared to be slightly different at certain time periods. This is likely due to not accounting for air resistance, assuming that the mass's weight was evenly distributed and plotting the mass as a singular point, and human error. There are two discussion questions that need to be answered. The first question asks you, for your model system, is the energy principle satisfied? The energy principle is satisfied in my model. This is because the energy principle states that the change in all energies added together are equal to the change in total energy, which is zero in this case. The graph of the model accurately shows how all of the energies working on the mass move the total energy to zero. The second question asks you to, using the data you obtained in Tracker, make two separate estimates of oscillation periods. First, by estimating the period of oscillation from the X position data, and second, by estimating the period of oscillation from the Y position data. From the X position data, I got an oscillation period of 1.74 seconds, and from the Y position data, I got an oscillation period of 1.215 seconds. Comparing the two periods, they will have two different Ks values as well as spring force values, as these values are dependent on the oscillation period.